Hi everybody, my name is Blake Perez from Intopology. I'm the APAC manager for the company, and today I'm excited to talk to you about digital engineering tools for the future of design and manufacturing. So design software is now the bottleneck in advanced manufacturing. So what I want to do here is explain to you the opportunity and the problem that Intopology is helping to solve. Since the 1980s, manufacturing has really changed. The way we manufacture things is very different. Additionally, the computers that control that process have advanced in many ways. However, the digital engineering tools have failed to keep pace with this speed of innovation. And so design software today, in many ways, is the same as it was 30, 40 years ago. And so this is where Intopology comes in. And I want to talk a little bit about what we do, right? So we built Intop platform to solve complex engineering problems. And the reason we do this is we really wanted to empower engineers to design transformative products that we've never seen before, never been capable of before. And so Intop platform is a computational modeling software for design, simulation, and advanced manufacturing. And there are sort of three main tenets or value propositions of Intop platform. One is unbreakable geometry. I'll talk about that in depth later. This concept of field-driven design that is, I think, new to the industry. And finally, reusable and remixable workflows, the way we're able to capture engineering knowledge in the software. So when I say unbreakable geometry, what I mean by that is the way we handle geometry, it enables fast and complex design and really reliable modeling operations. So basically models that won't fail, no matter what type of inputs and parameters you give to them. Second is this concept of field-driven design. So field-driven design unifies simulation, design, and manufacturing in a way where you can drive part performance with this. So the example on the screen here is simulation data being used to drive the geometry of a lattice structure. And finally, when you put these two things together, unbreakable geometry, field-driven design, you can create reusable and remixable workflows. So we can capture engineering knowledge, repeat it, and share it within an organization. What you see on the screen here is lattice structures and medical devices being applied to different parts in a product family. So all of this is great, but how is Intopology different from other engineering software? Right, so it really comes down to our implicit modeling kernel, which lets you design without boundaries, quite literally. So on the left, we have our standard boundary representation of a CAD model, and then on the right, we have the implicit representation of a three-dimensional volume. So this is a two-dimensional example, and you can imagine that it gets more complex as you move into 3 dimensions. But with a boundary representation or a mesh representation, you have a bunch of surfaces that are knitted together to define a volume or define a shape. And a lot of computational power is wasted on making sure that these edges, these surfaces are knitted together nicely. Whereas in our implicit representation, we use a single mathematical equation to define a volume. So not only do we have the boundary of this circle, but we also have additional field information about the inside and the outside of that. Sine distance function is what gives us that information. And so as we start to do things and with our modeling software, when complexity grows, implicit stays simple, whereas boundary representations, traditional CAD models get very complex very quickly. And we start wasting more and more computational resources to make sure that our surfaces are knitted together, that there are no gaps, there are no intersections. And of course, this gets even more complex when you want to change topology. You want to make model updates and change the parameters of your underlying model. So when complexity grows, our implicit stays simple. Right, so boundary representation, it's complicated. Implicit representation always stays simple. And so regardless of complexity, our implicit modeling kernel just works, and it really expands the realm of engineering possibilities. So here's a few examples of what Intop has delivered 10 times faster. So this is a project, design time to a flight qualified part. And these are all from customers, from case studies, things that have happened with the software. 2x the stiffness at 50% lower weight. So making parts stronger, even though we're using less material and making them lighter weight. 48% lighter. This is from an aircraft part that was optimized with Intop platform. 300% better thermal performance. This is from a heat exchanger that was designed in the platform and additively manufactured. 4 hours. And so this is 4 hours compared to what used to take engineers 6 days with legacy engineering software. 200,000 heat exchanger coupons produced in minutes. So because of this reusable, remixable workflows, we can create multiple iterations of a design and actually simulate those, maybe even print them and test them. So we also have, when we think about how usable is the software and its usability, 2 days is the typical training period for Intop users to become comfortable with the software. And then of course, after 2 days, you begin that journey into becoming an Intop expert. And so this is the capabilities of the software and the platform that we provide. I want to talk a little bit about the company, who we are, and how we're able to support this. We serve 4 key verticals today and continue to grow: aerospace and defense, medical, automotive, and consumer products. These are where we see the most uptake and utility of Intopology software. We've grown a lot over the past few years. We were founded in 2015 in New York City. We launched our original product in 2016, and building on the learnings from that, we launched Intop platform officially to the public in spring of 2019, and that enabled us to capture a $20 million Series B funding round, wherein Carl Bass joined our board of directors, the ex-CEO of Autodesk. And we also kind of launched a new version of the software in 2020, more applications focused in what people are using today. And that, of course, led the way for our recent announcement for another $40 million Series C round, which was led by investment partners in New York City. And we've caught the attention of industry experts. So Blake Corder, the founder of SpaceClaim, is our CTO. Steve Costello, previously from Aras and SpaceClaim, is our CRO. As I mentioned before, Carl Bass from Autodesk is one of our board members. And we also work with George Allen. He's our Intop fellow, and he spent over 40 years with Unigraphics and NX, really living and breathing modeling. All right, and so that's a background of the company. What about the applications? What can you actually do with this, right? So I wanted to talk about, where customers use our software. One of the big things is lightweighting or material reduction for additive manufacturing. You want to make parts lighter, or you want to use less material. The reason I wanted to show this slide is that we help people lightweight parts, but we give you so many ways to do that. Whether you want to do topology optimization, some type of infill, some type of shelling operation. Maybe that shelling is variable based off of simulation data. Maybe you want to perforate the part with 10, 100 thousands of small holes to make it lighter, or some type of lattice infill, and combinations of different variations of these. You always have the right tools at your disposal based on your geometry here, is what I'd like to show. And so based on your application, Intop platform gives you a toolbox full of tools to help you reach that goal. And we also do a lot of structural optimization. So the part that I'm showing on the screen is an automotive bracket. Here it is a hollow part. So we've created a part and we've created it and turned it into a shell of a part. And the thickness of the wall of that shell is actually driven by engineering data. So you can see the simulation data on the right, you can see the part on the left, and areas of high stress are thicker, whereas areas of low stress are thinner. So this variable shell operation, I think, is actually very incredible. I haven't seen this done in any way in traditional CAD tools. So structural optimization, we also see some utility in medical, right? So I mentioned this before in reusable and remixable workflows. Being able to design a lattice structure, and let's say you do some research to ensure that this lattice structure is really good for the human body, maybe bone grows into it really nicely. You can take that lattice structure, you can take those parameters and repeat it on different products, different geometries within a product family. Right? There's also utility in industrial design and part texturing. So designers using our software to create patterns, capture a design language, and deploy this design language to multiple different parts. And so I want to talk through, lastly, a few examples of Intop software being used. So here's a gas mixture handling pipe. It's been reinforced with some stiffening ribs, and thickness and the height of these ribs are driven by simulation data. They also conform nicely to the surface. And in this part, we actually took an assembly that was, I think, almost 40 parts and turned it into a single component that is additively manufactured. You can also see certain regions of this component have also been topology optimized. So we're bringing in these conformal lattice and rib structures, some perforations on the left side, if you can see, as well as topology optimization, all into a single part. And then on top of that, of course, part consolidation. This heatsink uses a graded infill structure that is self-supporting, so it's very additively manufacturable. But then also you can see at the bottom there, the gyroid structure is much thicker than at the top, and so this is a nice wider conductive pathway for heat to move from the chip surface up to the top. And then this gyroid structure also enables lots of turbulence of the air flowing through it to reject more heat out into the surrounding environment, giving us a very high performance heat sink. And finally, I really like this part. This is a brake caliper designed by one of our partners in Japan, Yamaichi Special Steel. So it uses topology optimization to control the thickness within the part to make it strong enough for the engineering requirements. And then you also get this really interesting aggressive look. So you can kind of define, you can have an engineer working together with a designer to define a design language, but also make sure that that part, while aesthetically pleasing, also meets the engineering requirement of the part of the product. And finally, some COVID-19 test swabs that were designed in INTOP platform. And the goal here was the research team was trying to understand what type of lattice structure, what thickness of lattice structure, what density would be most comfortable, would also survive the testing procedure. So we were able to design and fabricate hundreds of these over a weekend to actually do all of that testing and make a swab that was ultimately put into production and used. So thank you very much. My name is Blake Perez, again, the APAC manager of INTOPology. If you would like more information, please feel free to reach out to me directly. You can also visit our online resources, our YouTube channel, our LinkedIn to find out more about the software. I also want to mention Harvestance. So Harvestance is our local partner. They are designed for additive experts, and they can also answer any questions that you have about the software, as well as provide localized training. So thank you again for your time. I look forward to hearing from you in the near future.